Welcome to CS253 Web Security, Lecture 2. Today we're going to talk about DNS, HTTP, and cookies. So first, some quick admin stuff. So assignment 0 is out. You can go ahead and access that on the website. And I decided to drop one of the assignments in the class, so we're going to have a total of 5 assignments. That includes assignment 0. So after you finish assignment 0, there's 4 other assignments. And office hours this week are going to be, for me, today at 3 to 5 and Gates 3 to 23, and Esther's having her office hours on Friday from 1 to 3 in Huang Basement. So let's start with considering what happens when you type a URL into your browser and press enter. So this is actually a really common interview question that is often asked at internships in Silicon Valley, but it's also a good way for us to start to think about what actually goes on in the browser, and what this will set us up nicely for thinking of attacks on this process in the future. So when you type a URL and press enter, this can happen, but really what actually happens is the first step is a DNS query. So the DNS system is a system that translates user-friendly domain names into IP addresses. So IP addresses are the way we address all nodes that are connected on the internet, and a domain is a friendly, human-readable string that we like to type into our browsers. And so we need to do this translation step as the very first step, because the browser doesn't know which server to contact until it does this translation. So we'll go ahead and walk through that process so we understand what exactly goes on. So at a very high level, your browser makes a request to some server, which we call the DNS server, and the DNS server gets this message from the client, and it's in the form of a query. So the client is asking a question, and the question is, what is the IP address for a particular domain? In this case, Stanford.edu, and the server is going to respond with the IP address for that domain. So that's the high level. But what is that DNS server actually doing? So this is a more detailed view of the process. So the client is going to we start off by sending that same query for Stanford.edu to the DNS server, but we're labeling this DNS recursive resolver now, because what the DNS server does is it actually does a bunch of work on the behalf of the client when it receives this query, and we're going to take a look at what it's actually doing. So the recursive resolver is going to take on the responsibility of looking up the IP address for Stanford.edu and doing whatever work is necessary to do that, and then it's going to get the answer and send it back to the client. And this process might take multiple steps, and that's why we call it a recursive resolver. So this server is going to actually continually make queries to various other servers until it gets the final answer that it's going to give to the client. Right, so anyway, there's these root name servers, and these are hard-coded into every DNS resolver, and they're run by different organizations. And so a recursive resolver is going to go and ask that root name server for Stanford.edu. It doesn't know the answer because, again, like this is a problem. There's just a problem with scale here. Like a single server can't keep the records for every single possible domain in the world. But what it does is it delegates authority to another name server that's responsible for just a sort of subset of the names. And in this case, the EDUs are all managed by a different name server. Now, the recursive resolver is going to just go and ask the same question to the EDU name server. And again, the EDU name server is also not able to handle a listing of all this stuff. And so it's going to respond with, well, go and ask the Stanford.edu name server. And we go one level again. And this name server, fortunately, can actually respond. And so this is what's called the authoritative name server. It actually knows the answer to our question. And it will respond with Stanford's IP address. Cool. Pretty straightforward. What's worth noting here? This is sometimes called the TLD name server because it's responsible for the whole top-level domain of EDU. Let's see, anything else I want to mention about this? I think that's it. Any questions? How many people have seen this before? Maybe. Okay. Yeah. Cool. So now we have at least a partial initial answer to the question, what happens when you type a URL in? So we do, we talk to this recursive DNS resolver. It's going to go and talk to the root name server responds. Then we follow up, the recursive resolver follows up with the TLD name server, which responds. And then we go again until we hit the Stanford server, which finally can respond with the IP address. Cool, so now let's throw an HTTP into the picture. So this is what it's going to look like. We're not done when we get the IP address of the server. Now we actually have to connect to it. So now when we get the IP, we now know, this is the server we need to talk to. And I guess I changed the IP address here, but this is the Stanford IP address. And once we know it, we're going to make an HTTP request to it and get back a response. Cool. So now, given this picture, can anybody tell me, can you think of any kind of an attack maybe on this architecture? If you were trying to attack like a visitor who's visiting stanford.edu, what's something you might do? Could be anything. Mm-hmm.
If we can somehow change that number that's being returned from the DNS recursive resolver, so that the computer would think that this other IP address would belong to stanford.edu.
Yep, totally.
When you type stanford.edu, we go to that other address.
Yep, that's right. Yeah, and so you'd be connecting to the wrong server in that situation. That particular attack is actually quite easy to do because these queries are in plain text. So anybody who's any sort of device on the internet between you and that recursive resolver can insert itself in there, and when it sees that you're making this query, it can just decide to not pass that query onward to the next node in the network, and it could just itself respond to you. And then you'll go ahead and connect to the wrong server. That's totally right. You had another idea.
No, I was thinking you can attack the response that the server goes back.
This particular HTTP response?
Yeah, is that possible? Like modify it, insert some sort of.
Yeah, that's totally possible. Yeah, so that's. Do you know the defense against that?
No.
Okay. Anyone else want to volunteer that? Yeah.
TLS.
Yeah. So we're going to have a lecture on TLS, but basically TLS is encryption. It's when you see HTTPS in your browser, and what that gives us is a couple properties that are really important. One is integrity, which means that the response can't be modified. If it's modified, then the client will be able to tell. And the other one is authenticity, which ensures that we're talking to the server that we think we're talking to. So if anybody were to try to insert themselves in there, like you suggested, and send back a different response, we wouldn't trust it. So that uses signatures, which if you want to learn more about, you should take 255, which is an amazing class. But yeah, so yeah, we can interfere in the HTTP process or in the DNS process. Totally, those are both valid things. With HTTPS, of course, like I said, we'll be able to detect that somebody has sent us to the wrong server. But one thing that's interesting is, let's see here. So yeah, if you've inserted yourself in here and here, actually I have a picture of it. Oh no, it's later. Yeah, we'll just get to that in a sec. So just to review some of the stuff we talked about. So right, so you can change the DNS records of the target domain and point it to your own IP address. And now when visitors go to the site, they're going to be directed to the attacker's web server. And the motivations for this are like now, you can basically load anything you want, and the user's going to potentially think that that's the original site. So that's called phishing. And you can collect users' passwords or whatever you want to do. There's also money-making things, like there's these JavaScript crypto miners, which are pretty hilarious. Basically, it's a bit of JavaScript code you can put in someone's, put into a web page, and that's going to actually try and mine. Typically, I've seen it. They mine Monero for whatever reason. I think because it's easier to mine that on CPUs. I think that's the reason. But anyway, it's pretty hilarious because you might be on a laptop, which is not very suited for mining cryptocurrency. But the attacker doesn't care because even if they can make like 5 cents and burn $3 of your electricity in order to do so, that's still 5 cents of profit for them. So that's kind of a pretty hilarious attack vector, or an attack that we see in the wild. And then of course you can just change the site subtly, including ads in the page or something like that, and it's another revenue source. So how do you actually go about doing this? There's a couple of different places you can affect DNS. So one is directly on the user's system. So if you have malware on your machine, the malware can go in and just change your local DNS settings so that it's going to basically route a domain to a different destination than it should. You can actually just do this yourself on your own computer. If any of you have ever modified the Etsy hosts file before. That's a way to basically say, whenever I do a DNS lookup on my computer, I don't care what the true answer is. I want to hard code in this IP address as the answer, which can sometimes be really useful if you're testing, like you're trying to test your website and you want to just say like, okay, always point it to my own computer when I type in my domain name or something like that. But malware can go ahead and change that, and that's really not good. You can have the DNS resolver itself get hacked, and typically you're using the DNS resolver that comes from your internet service provider. So in the case here at Stanford, it's just Stanford has like an IT team that provides this for us. If that server were to get hacked, it could just start giving out wrong answers to everybody, and our browser's going to go to that wrong IP address. You can also have hacked routers and then the DNS name server itself. So that's the actual the thing that's responsible for, let's say, Stanford.edu. If that thing is hacked and is just going to give out the wrong IP address, that's another issue. And then lastly, like you might have a company that you're paying to provide this DNS name service for you, and if your account there gets hacked, then somebody can go in and of course just change stuff. So this is the flow in that situation. So you have a hacked DNS resolver. You have the request goes to it. It responds with the incorrect IP address, and then your browser just connects to the malicious server, and there you go. So we mentioned HTTPS might help us here. So how might HTTPS help us here? Anyone have ideas? Yeah.
Since HTTPS provides authenticity, you would know that it's the malicious server, not the real server.
Mm-hmm. That's correct. Yeah. That's so to repeat. If your browser's expecting to get back a certificate that says, we'll talk about this stuff later. We're getting a little ahead of ourselves here by getting into the details of HTTPS, but I think it's okay. So if there's a way that this server could, where the browser expects the server to prove itself to the client before it trusts it and before it sort of gives you the lock in your browser, basically, then we would be able to know this happened. The interesting wrench that gets thrown in here is that there are services like Let's Encrypt, which provide free certificates to anyone who can prove that they are in control of a domain, right? And so if the attacker is able to make it so that when Let's Encrypt or any provider who's going to issue these certificates, if they can make it so that when they go and check, like, what is the server that Stanford.edu is pointing to, and they get back this wrong answer, then that provider is going to now connect to the wrong server, and it's going to issue this challenge to the server. It says, prove that you want me to actually issue a certificate right now. And the attacker will say, yeah, of course, issue the certificate. Give me that, please. And now they have a certificate that they can provide in this response that will make your browser trusted. So this is actually really bad. Even HTTPS, in the way it's normally used, can't help you at all here. So it's really bad. So does that make sense to everybody? Any questions? Yeah.
So are you saying, so I'm not that comfortable with certificates, like I do not understand the concept well. So when you say, so what happens is your malicious server somehow gets an actual certificate from that company that you said, or that organization that you said?
Yeah, so we'll have a whole lecture on this, so apologies for getting a little ahead of myself here with this, but basically the way to think about it is there's a company which, if it can prove, if you can prove to the company that you're in control of a domain name, right, then they're willing to say, okay, we proved, like we're convinced that you own this domain. So what we're going to give you is basically a file. It's just a text file that's a certificate that you can now, that person who owns that domain can now attach to all the, basically attach something to the response that they give to everybody. And now the client can know for sure that the person who sent this response is in control of this of the private key that goes with that certificate. And so basically they're the person who's actually running the server in question. And so that's important because on the internet, it's like all these requests and responses are getting jumped around over many nodes, and a lot of these nodes are controlled by completely different entities than the client or the server. They're just random companies. Or government agencies in some case can affect those nodes, and they can modify those requests, or like we were saying before, insert themselves in and send a different response. And so if they don't know the private key that goes with that certificate, then they won't be able to do that, right? That's kind of the idea. Does that make more sense? Yeah. Okay. Yeah, we'll have a whole lecture on it. Cool. In fact, I'm trying to get Dan Bonet to give that lecture because I think he'll do a really good job of that. But yeah, he might be one of our guest speakers. We'll see. He's really busy. But yeah, okay. So just some stuff in the news about this. So a ton of education, like a ton of universities and schools and stuff are affected by these kinds of attacks, and mainly it's to steal people's personal information. So if you can convince, if you can trick like an administrator to go to a different site and log in there, and then you can get their credentials and steal everybody's socials and their payment information and stuff like that. And a lot of schools don't invest in their IT infrastructure because they're not funded very well. In some cases, it's like one person who's like responsible for a whole school district or something like that. And so there's just like lots of misconfigurations and weak passwords, and people just haven't like tried very hard to secure this stuff. So yeah, it's a huge number of attacks. Another place where you see this is internet service providers will actually do DNS hijacking. So you're moving your head up and down, Pierce. Have you seen this before in the wild?
Yeah, I've seen it a lot with like back in the day with like those browser toolbars. They would like hijack like domains that wouldn't have, I guess, that wouldn't be valid to point to their own search pages and like sell ads.
Yeah, that's exactly what this is here. So to repeat, what's going on here is that if you type in a domain that isn't valid, so it's like it should just return a browser error page to you. Like there's no actual server there. There's no record to find. What these companies are doing is they're saying, well, why don't we just show you a page that's like more useful than an error page, right? An error page is just like not going to help you, but we can show you a nice useful search page with lots of nice, I guess those are sponsored by, so on and so forth. So it's like, yeah, it's going to make them more money. The bad thing with this is that in this case, this is actually for a domain that exists, which is a web comment called questionable content, and they injected themselves in there anyway. So their implementation is buggy. So it's just a bad idea. Like this is like the kind of thing that an attacker is doing. You don't expect your internet service provider to be doing this to you. But yeah, you can. And actually, T-Mobile does do this to you. I have T-Mobile, and you can turn this off. If you go to the bottom, or there it is. Why am I here? You can tell them like stop this. But anyway, yeah, it's really bad. Comcast also does it as well. Yeah. Cool. So yeah, but in the case of the ISPs doing it, one thing that's nice is they're not going and registering certificates for the domains that they're hijacking. they're just responding with these error pages. If they were to try to do this to a site that was actually HTTPS, right, they wouldn't be able to provide that certificate to prove that they're the true owner of the domain, right? In this case, I think this is HTTP. You can see it there in the URL, so that's why they're able to return a page, and then the browser trusts that. Cool. Any questions about this? Cool. So yeah, let's talk about just a few of the privacy things that come up. So we talked about security of DNS, but privacy is also a big deal. So we talked about how the queries are in plain text, and if the server that's sitting there, that recursive resolver, it just wants to like log every request that you're making to it, they can do that, and they can produce these lists of domains that you've looked up, basically, right? And these companies, these internet service providers, have been known to sell these lists. So they'll say like, this internet subscriber, like frequents these domains, and that's obviously not something that you probably expect to happen, or expect a company that you're paying to be doing, but this is possible because of the way the protocol is designed and the fact that those queries are in plain text. So one like just personal trick you can do if you don't want this to happen is you can just set your DNS settings on your computer to a different company that you have to trust, again, but at least certain companies have posted privacy policies that say that they don't sell your stuff. In particular, this service right here, it's really easy to remember. It's 1.1.1.1. They got that IP address. That's a Cloudflare service which provides DNS that doesn't, they say, sell your DNS queries to companies. Mm-hmm.
I think on Android they now can also encrypt your DNS queries. There's like an option for that.
Oh, is that?
So the other people on your network can't see it even if they aren't your DNS.
Even if they aren't your DNS provider. Yes. I was about to mention that next. Yeah. So what you're referring to is, I think there's this sort of enhancement to DNS that's brand new that is being developed at the moment, called DNS over HTTPS. And the idea there is we want to encrypt our DNS query itself, so that people who are observing that query can't actually see it. So in this situation here, like going back a second to the way that, so I was suggesting that we all use Cloudflare as an example as our DNS provider. We're sending these queries, they're still in plain text, right? The difference is now, now Cloudflare, when it gets this query, it's going to not save a copy of it and sell it to somebody. It's going to send back the answer to us. But this communication is completely in the clear here. It's plain text, right? So again, our ISP, if they wanted to, could say, oh, well, you're not sending your DNS queries to us, but we see you're sending them to Cloudflare, and we can just see the query. So we're going to go ahead and still save that information anyway. that's the problem we're trying to work around here. So the solution to that is this thing that is called DNS over HTTPS. And the idea there is, well, let's just make a connection that's secure, that's encrypted, and then we'll send our query and get a response over that. And that sort of solves this problem. And Firefox just made this the default, so that's really nice. It's not getting Chrome or any of the other browsers, though some of them are starting to test it out. But yeah, this is really cool. And the reason why this is particularly cool is that even if you change your own operating system's settings to use this provider here, you end up the query still goes over unencrypted. So you want really DNS over HTTPS for your whole computer, but Mac OS and Windows don't support that. So the next best thing you can do is just have the browser do it until that's supported. Cool. Somebody had a question.
Oh no, I was just wondering what exactly is Cloudflare, and is it a free service or?
Yeah, they're a company that provides CDN services. So they basically take your site's content and can put it on servers all around the world, so it's faster. And then they just sort of provide a bunch of these other add-on things like DNS. And it's a good question, like how do they provide this for free? It seems like there must be some game going on there. I don't know, just do your own research and see. But I think they're legit. They seem good. But yeah. Mm-hmm.
Does DNS over HTTPS use TCP?
Yeah, I believe it does. Yeah. So I think the reason why you're asking that is because DNS is UDP based. Yeah, this would be using TCP. That's right. Yeah. So it's kind of different. Mm-hmm.
If I trust people on my network but not anybody else, what's the adoption like for my router? If I just want my router to do the actual DNS over to us and then respond to me in an encrypted way.
Yeah, you could do that. Yeah, so you can set up your router to actually do DNS over HTTPS, and then everybody who's after your router won't be able to see it, but then your local network it'll be whatever people are using. So you might reveal it to them. Yeah. Cool. So now let's look at our new picture. So what happens when you type in a URL? Let's get back to that question. And so let's focus specifically on the HTTP part again. So now we have our IP address. We know we know who we're trying to talk to. Our browser makes the request to that server, and it gets back a response. This is something you've all seen or done before, but we're going to just make a request here I'll make this bigger, to Twitter, and we can just see that's an HTTP request that we sent, and we just got back a response. Is that big enough for everybody to see? Yeah. So we're just making an HTTP request there. If we want to actually view that, we should probably save it to a file. Here we go. Save it to an HTML file, and now we can open that up, and we can see that we actually did. That's what we downloaded, and we can see the URL there is off of my file system here. So that's pretty cool. So yeah, HTTP requests, nice and simple. So that's what's actually getting sent over the wire. So that's just some text. There's just a couple things to point out. The first line is the thing that actually explains the request and the file we're trying the resource we're trying to request. And then we have these headers, which are just key values that are underneath it. So the first bit is called the method. The method is often going to be get, but there's also a few other types: post, put, delete. Am I forgetting any? There's a few others, I think. And then we request a path, and then we say what protocol version we're using. It's usually just going to be 1.1. There are newer versions of HTTP, like 2, and there's even 3, which is brand new, which is crazy, because 2 just came out. Before that, we had 1 and 1.1 for like 15 or 20 years. And now all of a sudden we have HTTP 2, and then a couple years after that 3. So the pace is picking up. The good news is almost everything still supports HTTP 1.1, which is the version that
that is like most widely deployed. And this is a really nice version because it's all plain text. So you can just type these requests out in textual form. They're very easy to read. That's not the case for the later versions. Cool. And then once we send this to the server is going to send us back a response. And our response is going to be a file that we actually want to view. In this case, it's this HTML here that I've cut off. But it's also going to be prepended with some information, some metadata. Yeah, so let's talk a little bit about so this is just the first line. So again, just confirming that it's speaking the same protocol. And then there's this thing called a status code. This is probably a review for all of you because you've all hopefully taken web class. But we have these status codes and these messages. So let's talk a little bit about HTTP. Why is it cool? So we have the client-server model. We have a client asks for requests from a server, and the server replies. It's nice and simple. And like I mentioned, you have this simple textual protocol, so it's very sort of easy to read. And the headers are really cool because they enable HTTP to be extensible. So you can add new features without having to change, get everybody to agree on a new addition to the protocol. You just sort of add a new key and value, and if the server doesn't understand it, it just ignores it, right? So that's pretty cool. And it's also stateless. So two requests that you make one after the other have no relation to each other. Last thing is it's technically transport protocol agnostic. What that means is basically that you can do HTTP over any kind of communication channel that you have. It doesn't have to be TCP, although TCP is what we typically use because that gives us like a reliable connection between two nodes on the internet. Cool. So any questions about this? Yeah.
So isn't the property of being stateless kind of like up to the server to enforce? Because you could say have a server that that doesn't expect stateless requests.
Mm-hmm. Yeah, that's right. So if you wanted to, you could make your requests. You could make the order matter or something. You could have a server which is like, okay, every 10th visitor is going to win a free prize or something, and I'm going to count the requests. And then of course now there's some state that the server is keeping. But the way I would think about it is that you're building that as sort of on top of the HTTP protocol. The protocol itself isn't keeping any state. So if you just say, give me HTTP, you're not going to have any kind of state that's being kept by the server. It's all sort of discarded. And if you want to sort of on top of that keep state, you can. Yeah, that's a great question though, because typically when we interact with web services, there's some state. When I click a link, when I log into a website and then I start clicking links, those later links that I click, I'm still logged in, right? So clearly the server remembered something about me so that I could continue to view different pages and still be logged in. So we'll talk about that at the end here, and that's cookies. Cool. Oh yeah, so there's a slide for that. Yeah, so HTTP is stateless. We implement state on top. Cool. So just this is probably again a little bit more review, but we have these different categories of status codes. So everything in 200 is what you're going to see a lot of. That's basically the server saying that the request that you made succeeded. Anything in 300 means that the server's redirecting you to another destination. 400 means that you messed up, and then 500 means that the server messed up. That's the best way to think about it. So yeah, just a few highlights of the most important status codes that you'll see. Something fun?
Just a less censored version of your last slide I saw on Reddit the other day.
Oh, really?
Yeah, and I just saved the picture for it.
Oh, is it like you effed up or something?
Yeah.
I might have seen that same one. Yeah. Anyway, so yeah, there's two main types of successes. So 200 is the most common, but there's this other one called 206, which is given in response to a range request. So you can make a request for a partial subset of a resource, and then the server can say, okay, I'll slice that part of the file off for you and give that to you. Can anyone think why that's useful? Where would that be used? Mm-hmm.
SoundCloud uses it for parts of, to give you small parts of songs so you don't get the whole thing.
Yeah, that's right. So say you wanted to seek to the middle of a video or a song, and you just click in the middle before the browser's actually downloaded the whole video file. It would be nice if the browser could say, I know I want this file starting at byte offset, 100,000 or something, right? And then you can make that request to the server, and the server can respond and say, okay, there's the piece that you asked for. So you don't have to wait for the whole file to download sequentially. That's really useful. So that's called a range request. And then 206, the reason why we do 206 responses there is because say that you make a range request to a server and the server doesn't actually understand range requests. Because remember I mentioned you can add these headers and the server might not know what the header means. It might be like a simpler server. And if a server doesn't understand this range header that you tacked onto your request, it won't know what to do with it. So it'll just respond with 200, here's the whole file. And then your browser needs to be able to know, oh, okay, I was not expecting a 200, I was expecting a 206. So this is clearly like a server that doesn't know what I asked it. And you need to sort of adjust your behavior according to that. Cool, so then some 300s ones, so there's 301, 302, which basically are just a typical standard redirect to another URL. The difference between them is that if you do a 301, actually, does anyone know the difference? I mean, it says up there, but what is the actual behavior difference when your browser gets a 301 versus when it gets a 302? What is it going to do differently? I mean, can you just maybe? It's okay. You can just guess. Yeah, in the back.
I would guess that the next time you request it, it goes straight to the new one. It's permanent.
Yeah, that's right. So it won't even bother checking the original URL. So if you like reload the page it's basically doing is saving an association. Like when I see this URL, just don't even ask the server. The server told me it's permanently at this other place. I don't have to. But if it's temporary, it's gonna ask it again because it could be that now it's in a different place, and every time you ask it, it's gonna give you a different place, right? So actually, I implemented some random functionality on a website that I have, and if you do it with a 301, it doesn't work. So what you want is like every time the user goes to /random, you want to send them to a random page of the website. If you do a 301, then anytime they click random, it's going to just take them to the first one that they got sent to, right? So that's an important difference for that kind of functionality. Cool. And then for 304, this one is this is used when the browser has cached a resource and it wants to tell the server, hey, this is a file that I already have, but this is the version of it that I have, and like tell me if only respond if it's changed. So you can make this sort of conditional request where you say, so you're either going to get back a 200, which means that the request has indeed changed and the server is giving it to you, right? Or if you have the current latest version, then it will respond with a 304 and say, it hasn't been modified since you last got it. You do have the latest version, and it won't actually send it down to the browser. Just saves some time and bandwidth for us. Cool. Any questions about these? Yeah.
When would that be returned? Because like if you make a query and you get status 200, you try to make the query again, you like get status 200 again, or like
yeah. So
configure that.
How would you configure? Yeah. So in the actual request, you're going to add in a header. I'll actually get to that in a sec. But you add in a header that says this is the version I have, and then the server can sort of see that, and it can go and check, has it changed since you... So you can actually say, like, you can even do it by date. You can literally say, the version I have was given to me at this time, and then the server will only respond to you if it's been changed since that time, right? So you do have to change the request that you make. If you don't include that, it's always going to just give you a 200 if it's there. Yeah. Cool. Cool. Okay, and then the errors. So these are just different variations of that the client gave the server a bad request. It might be that you don't have permission to access it, or you don't have the right password or something. And then 404, we've all seen that. That's just that the URL is wrong. But the important thing about these is that it's the client that made the mistake, right? So if the server makes a mistake, you're going to get a 500. And so this is like sort of the server telling you like there's some kind of like uncaught exception, for example. You'd get back a 500 in that situation. These last three are interesting because they have to do with proxy servers. Let's see. The thing I'll say about that is just that it's often common in the real world to configure a whole swarm of servers, like a whole bunch of them, and then you want to have them all appear to the user as one server. And the way you do that is by having a server sit in between. I actually have a picture of it, I think, somewhere here. There it is. Yeah. So yeah, so you can have a situation where back here you have potentially hundreds of different servers. This is how big web services scale. And then the user doesn't know about like which particular server they're talking to, but they send a request to the main server, and that server proxies through the request to a backend server, right? And you can imagine a lot can go wrong at this stage here, right? So what if the server that the proxy sent the request to is down? How long should this proxy wait for a response, right? What if, and there's all kinds of different ways this can fail. What if, yeah, so it could be that the server is online, but it's behaving poorly, so it's like really slow, right? And maybe we want to configure the proxy so that it has a timeout where it will just give up after a while because it doesn't want to waste one of its connections on this never-ending request. And so there's all kinds of ways it can fail, and that's why we get those different codes there. So like bad gateway is the server's down, service unavailable means it's temporarily down or overloaded, and then timeout is it took too long, basically. And there's a bunch more of these, but so why do we have these special code numbers? What's the point? Like, why can't we just put a message in the response that says what went wrong? Why are we also adding a number to the response? Mm-hmm.
So it's easier for programmers to like code how to deal with these different things, so it's kind of standardized. So that like if one server says server is a proxy, like whatever, and another person says that, but with synonyms, you don't have to like do natural language processing.
Exactly. Yeah, so like if I see that I got a 404, I won't try that again. Like the resource is not there. If I get a 500, maybe I'll try that again. The server had an exception. I don't know. Maybe it'll work later, right? But yeah, the errors tell you different things. Cool. Yeah, and then these proxies are used for a lot of different situations. The one we just talked about is this one right here where it sits in front of many servers. But you can also have a proxy. Who's taken 110 in here before? 110? Okay, yeah. So yeah, I know you all know about proxies. But the kind of proxy you did in 110 is a client-side proxy. So that was a server that sort of it does the exact same thing we saw there, but this proxy is not run by a company that owns all these servers back here. It's run by like it's a program on your computer, or maybe it's run by your employer, so your employer can filter out certain types of websites so that you can't get distracted at work or whatever. Yeah, leave it at that. So back to HTTP requests. Yeah, so I want to talk about headers now. So we have a couple here, the host and the user agent, but the general format is it's a name and then a colon and then a value. That's how it works. So these let the client and the server pass additional information that's not actually part of the response. And it's basically a map of keys and values. And like I said before, it's really cool because it lets you just sort of throw in additional headers in there without getting all the browsers and everybody to agree on changing HTTP. So just a few highlights of useful ones that you're going to run into that you should know. The first one is host. That's the one we saw before. So that was the one that was right there saying hostexample.com. That one's really important. Most servers won't even respond to you if you don't include that. So that's just the name of the server that you're trying to talk to. And then there's user agent. That is the name of your browser and operating system. So that lets the server know who's the call-in basically at the server. This is actually really useful for detecting like when when a visitor is a search engine. So like for example, when Google requests a website, it'll say I'm Googlebot. It's actually what it's called, Googlebot. And then the server can know, okay, that's Google crawling my website. I can see they're visiting that URL and that URL and that URL, and that's pretty interesting. You can just, if you ever have a server, you can just look at those requests coming through, and it's fascinating to see the different user agents that are visiting your site. You can really, there's lots of random startups that have like really weird names that are like trying to build Google competitors, and you can see them crawling your website, trying to download pages. You can see when someone's using curl, like I just did, right? And you can actually sometimes use this to block requests that look malicious or where someone's misbehaving. Like the other day, someone was running a thing called like Site Slurper, trying to download like one of my websites entirely, just slurping all the pages down. And I just said, okay, if user agent includes Site Slurper, like no, just. But yeah, anyway, there's some stuff you can do. Now, obviously, they can control that user agent header, so it's not that good of a defense, but it's something at least if they're that obvious. Yeah, okay, and then refer is cool because that tells you basically the page that the user was on before they requested this page, right? So that's really interesting. That's how you can figure out like how a visitor got to your website. who linked them there, basically, and you can see how many people are coming to your site from that other destination. And then, like, obviously, notice I mentioned here it's misspelled. So the time when they were making this, the spell checker on like Unix or whatever system the person had didn't have either this spelling or the other spelling in it at all. Like, it just didn't know about the word refer. So the person just spelled it wrong, and then from then on, everybody was like, we could change it, but then we all have to change all of our code, and let's just leave it. So now if you read about HTTP, like all the specs and everything, just have it misspelled. That's just what it is. In the HTTP world, that's how refer is spelled. Yeah. What was that? That someone said something. Anyway, but yeah, so it's like sometimes it's just not worth the cost, the pain, just for some aesthetic thing. And that's actually the story of the web, honestly, is like anytime they can make a decision to like do things right or do things like easiest, they choose easiest, right? Because it's better for compatibility, it's better for not breaking old websites and stuff like that. So yeah, so there's good arguments for it. But yeah, it's also kind of gross. Okay, and then cookie. So we're going to talk about this if we have time, hopefully. But yeah, so cookie is basically it's a header that you attach to your request, and it's basically the server gives it to you in a response, and then the idea is once you've gotten that, you just tack it onto every request you make in the future, right? So we'll see the corresponding one that goes with this. So there's a header that the server can give you that's called set cookie, and then some value. And then when you get that, you basically save that on your machine. And then anytime you go to that same server again, your browser will just tack it onto the request and say, this is what you gave me before. Here's the cookie. Okay? And that's how you stay logged in. The server gives you some kind of a token, and then you tack that onto your requests. And then the server's like, okay, that's you. Right? And then range, I mentioned that before. So that's how you subset a request. And then there's a whole bunch more here. You can control the cache. You can say, only give me a response if it's been modified since this date when I got it before. You can control the underlying TCP socket. That's kind of crazy. You can say, like, when this request is finished and I've gotten the response, don't actually close the connection to the server. Keep it open, because I might send more requests over that connection. That's a performance thing. And then you can also say, like, what kinds of response you can accept. So you might say, like, I only want HTML back, please. Or like, if you want, you can gzip the response, which will compress it. You can tell the server, like, I understand how to ungzip it, so feel free to gzip it. You can also say, I want a particular language back, and it'll change the behavior based on that. So cool. I'm going to show just doing that really quick. So we can actually curl has a nice way of doing that. You just say curl. Twitter.com. Can't type. Twitter. Oh my gosh. Okay. Twitter.com. And then we say header. We can say accept language. And let's try to get back a Spanish response. So if I do that, the problem is there's all these tags, like all the trending hashtags are here. So like Lion King or something. But what I want to do is I want to just filter this out and just look for a particular phrase that I happen to know is in there called JavaScript. And I can also add silent here to get rid of the output with the downloading. So now if we do that, we just get this little part here that's telling you, who knows Spanish? Does someone translate this for us? What does this say? Mm-hmm.
We detected that JavaScript is disactivated in your browser. Do you want to continue on the old version of Twitter?
Okay, so it's giving them a link to click to go to the old Twitter that doesn't need JavaScript. Cool. So, oops. So now if I change this to like AR for Arabic, we'll get some cool Arabic script. Yeah, and you can just put anything there. But yeah, that's kind of cool. So it's just that easy to attach headers. Cool. Cool. Now let's talk about the response headers. So the server can tell you a bunch of useful things in the response. One thing. So here's a few we'll go over. So date is just when the response is coming back. Last modified is like when the file was last changed according to the server. You can use that in your future requests to say only give me if it's changed since then. And then again, you can control caching behavior. So you can say like, please never cache this. That might be something you would want to say if it's some information that you don't want to be saved onto the user's machine. And then expires is a way of saying, please delete it from your cache after this date because I know that I'm going to have a new version then, so just don't save it after that date. Very is interesting. So let's see. So very, has anyone seen very before? Like, or know what it is? It's really interesting. So so can you think of any problems with caching stuff? Like, say that I visit Twitter, right? And I set my language to Spanish, and Twitter sends down like a page, and they say like, go ahead and cache this for a day. Like, we know it's not going to change. The site will be faster, so just cache it, keep it cached for a day. And then I log out, and somebody else uses my browser and logs in, and they have Arabic as their language set. And now they make a request for that page. Right? The issue there is that now that request might match that page that's already in my cache that is in Spanish, right? And they're making the exact same request. They're requesting, say, the home page, right? And so how does the browser know that it shouldn't reuse that cached version that's in Spanish for the Arabic page request, right? So that's what the very header is for. So what would you do? Well, how would you use the very header to fix things? Anyone think how you do that? Mm-hmm.
You'd include, I guess, the accepts header in very.
Yeah. So you say here which headers are let's say how do I word it? Basically, yeah, which headers affect the response. That's what it says here. So you'd say like basically if so when you save this when you save this and cache it, remember to look at the list of headers that are in here and save that along with it. And next time you make a request, compare and see if the headers aren't exactly the same, then you need to not use the cached version, right? Does that make sense? Yeah, cool. Cool, and then set cookie, that just lets you set a cookie. So, the value is the cookie that the browser saves, and we'll talk more about that in a second. And then we have location. So that's useful if you're giving back a 300 response and you're going to tell the user to go somewhere. You do that by setting the location header. So when you get back a 300, the client looks at the location and then it goes to that destination. And then these are all just the sort of corresponding ones that match the things in the requests. So if you said, I want HTML, the server can respond and say, confirm, here's HTML, right? Or if you said, I want a gzip's response, it could confirm to you, okay, here you go, here's a gzip response. So you should make sure you use this to basically figure out what to do with the response. Cool, and so diving in here, this is just sort of the protocol stack. So I'll just expand the names there. So everything's is built on top of IP. That's just the way we connect two computers to each other. Oh yeah? Mm-hmm.
Quick question about the response headers.
Yeah.
So for things like cache control, is the client required to follow the headers? They are not. Is that correct?
Yeah, so they're not required. I mean, you could write your own HTTP client. In fact, like we might do that in a future assignment. You can just do whatever you want. Yeah, you don't have to follow it. There's no enforcement of this. This is just sort of the server's telling you if you want correct behavior, basically, you should do this. Yeah. Yeah. Cool. Yeah, so anyway, the important point here in this diagram is just to know that HTTP is built on top of a stack of other protocols. So the first step is you have to know the IP you're trying to talk to, and that's what we use DNS for. And once we figured out the IP address, we open a connection, use TCP for actually ensuring reliable and ordered delivery of our messages. And then this one here, TLS, this is encryption, so we're going to talk about that later. But note, this is optional, right? You don't need to actually use TLS. And then HTTP is what you actually send over this socket that you created with TCP. And then HTTP is typically used to transfer website stuff. So that's HTML, CSS, and JavaScript, although you can transfer anything with it. But typically that's what we're sending to our browsers. Cool. So what I want to show you now is just a really fun demo. It's basically what we're going to do here. I have the stuff up here. Basically, we're just going to make an HTTP client, like from scratch. So it's not magic. It's really not that crazy of a thing to do. You just make a socket to a server. You know the server's IP address, right? You connect to it, and then you just send this text over it, and then you get back this response. And it's not magic. So it's kind of cool. So this is what we're going to do. This might be useful to you if you're not familiar with Node, but this is a package that we're going to just import, and what it lets us do is create TCP sockets. So we use it by doing net.create connection, and it's going to take in an object. Host is the IP address, or if we want to be lazy, we can just put in the domain name, and it will do the DNS step for us. So I'll put in example.com here. And the port I'm going to put in is does anyone know the port I'm supposed to put in here? 80. Yeah, so 80 is just the port for HTTP. That's just what it is. Yeah, so we're going to connect to port 80 of example.com. So then this thing gives me back a socket. And I'm going to take the socket and I'm going to write something into it. So let's write in a request. So I'll define a request here. And I'm going to use this weird string syntax that you may not have seen before, but this is called a template string. And we're not even going to use any of the templating features that it gives us. We're just going to use it because it lets us do multi-line strings. So I can use new lines in my string. So I'm going to type here get / that's the home page. I'm going to get the home page. And I need to include a host header. Otherwise, the server won't know what we're asking. And then I'm going to add an extra new line here. So I'm going to do 1, 2 new lines. That's how the server knows that I'm finished with the request and there's no more headers coming, right? Cool. There's something wrong with this, though. Did anyone see something wrong with the way I've defined this string? What? There's a new line where? The beginning, yeah. There's a new line here. I hit enter here. So really I should do that. But I'm just going to be fancy, and I'm going to just cut off the first new line. That way I can keep my requests like that. Now I can also note I can't tab here either, because those tabs are going to be included in there. So it's kind of weird. Looks weird, but there we go. That's a request. Okay. Now how do I get the answer out? So the easiest way is, so this object this object here, socket, is something called a node stream. So this is an object which will over time emit data that it's received from the server that it's talking to. So does anyone see what's going on here? The write call, what we're doing here is we're sending data across the socket to the server. And now to actually read the data out, what we could do is we could like listen to. I'll just do it this way. We'll pipe. And what we do is we have to tell it a destination where we want the response to go. And we can just do standard out. That's the easiest thing to do. So what we're saying is just print what you get from the server out, just like that. Cool, so now let's run this. What was it called? HTTP request. Cool. Oh no. The chunk argument must be one of type string or buffer, receive type object. Does anyone see what I did wrong here? I wrote the string and then I piped it to standard out. Standard out, write request. Does that look, do I not have internet? Could that be it? Nope, I have internet. Oh yeah, let's look at the error, yeah. Unhandled error, the chunk argument must be one of type string or buffer receive type object. That is some kind of a stream error. Why would I? What does? Oh, sorry, I meant slice. Sorry, I used the wrong function. Thank you. Yeah, I wanted to slice off the, yeah, sorry. Good catch. Who caught that? I appreciate it. Yeah, thank you. Yeah, cool. So now let's try it. No, not that command. This command. Okay, cool. So what did we get back? We got back, notice, we got back the first line, which tells us that our response that was 200, it was successful. Got a bunch of headers. And then we got a new line and a new line. And that delimits the headers and the body. And then this is our body right here. This is our response. It's HTML. Cool. Does anyone know why? Does anyone know why it's hanging though? Like why hasn't it? Most scripts will end when there's nothing left to do, right? Why is it hung? Socket's still open. Yeah, I didn't close it. Yeah, so I could close it if I wanted to, but or the server could have told me to close it if it added that connection close. Then actually, I don't know if Node will read that and close it for you, or if you have to do it. But anyway, yeah, it's not getting closed. So that's the issue. Cool. So one thing I want to point out is like, if I remove this host header, what's going to happen? You'd think the server would know what to do, right? Like I literally connected to the server with a socket. I sent it this request saying, give me the homepage, right? Why wouldn't it just give me the homepage for example.com? Like it's the example.com server, right? Shouldn't it know?
Maybe different domains point to the same IP address and they just serve different things depending on which host we're actually trying to.
Yeah, that's right. So just to repeat, it's possible that one IP address is hosting many domains, right? In fact, that's very common, right? You might have a server that can serve your blog and then this other side project thing you're doing and whatever. You might have 4 or 5 sites all in one server. They all have the same IP address. So if you don't tell the server what host you're interested in, typically it'll just error. It might also just pick one and send you back a random one. But look, I think in this case what's going to happen is it will just tell us it's unhappy with us. See, it'll give us a 400 bad request. And 400 means it was our fault. So yeah, we'll add that in there. Cool. So and then so just one thing I want to point out too is if we want to not rely on this module to do the DNS lookup for us, I think it becomes even clearer why we need host. So if I were to do DNS, require the DNS package here, we can do dns.lookup on example.com, and that will give us. Has everyone seen this syntax before? This is basically me defining a function, and these are arguments, and this is the body of the function. So what I'm saying is, look up example.com, tell me if there was an error, and so what I'll do, if there was an error, I'll just crash the whole process. Honestly, it's better than ignoring it. Like, at least you know there was an error. And then what do I want to do here? So I want to take, this is the IP address, so what I want to do is actually use that in here. I need to actually copy all this code and paste it in here. There we go. So, oops. Oh, wow. I have some really weird shortcuts. OK. So, yeah, so what we're going to do is look up this example.com. We're going to get back an IP address, and then we're going to connect to that IP address. This is an IP address. And then now hopefully it's a little clearer why we also have to tell it like what domain we're interested in here. So let's see if this code actually works. No. Oh, I put it in a different file. Right, sorry. I've been just doing it in the same file. That's fine. Yeah, we'll do that.
You deleted the socket?
The socket pipe. Oh, thank you. Cool. That's interesting.
Is there extra spaces?
Oh, yeah, now there's spaces here. Yeah, I mentioned that you can't have spaces there. Yeah, so that's the problem. That's nice. That's a nice problem to have. OK. There we go. Cool. Got my response again. So that's cool. Yeah, so you connect with an IP, and then you tell it the domain you're interested in. Any questions about this? Cool. Yeah, so HTTP is not magical. It's pretty cool. And it's really nice how you can just play with this stuff with Node. It's pretty low level. You can just jump in there and do this stuff. Any questions before I go on? OK, so one other thing I want to show you is the developer tools. This is obviously a really handy thing to know about. So you can, on any page, you can right-click inspect and pull this up, and you can go to this network tab, and we can just see the same exact thing we just saw. So if I refresh this, we'll see that we got these headers. We sent these headers, and we got back these other headers here in response. So this is just something to know that you can do this. It's really useful it's going to be useful in the next assignment. You can just jump in and look exactly what request the browser is making. So one thing I want to do here is I want to go to like a slightly more complicated website than example.com. Like if I go to Twitter here really quick, I'm not logged in, am I? OK, good. So if I go to Twitter, you'll notice that this first request here was made to twitter.com, got back at 200, and then a bunch of these other requests were made afterwards, right? Why did that happen? Mm-hmm.
Could it be like there's code in the Twitter page, like asking for more resources from other places, like ads and stuff?
Yeah, exactly. So the browser doesn't just make the one request you ask for. It gets back the HTML, and then that contains within it more requests for sub-resources, right? And so that's going to happen, and there's this sort of a bunch of round trips that can happen, right? So it's really important actually for site performance that you sort of minimize the number of round trips, but there's going to be at least like 2, because you're going to request the HTML, and then you're going to get a whole bunch of stuff like images and CSS files and JavaScript files that you're going to have to follow up with. So yeah, just know that. Yeah, so So yeah, we can review now. What do we know about what happens when you type a URL in and press enter? So the first step is the DNS lookup. We're condensing it down into one line here because we know there's the whole recursive part that it has to do. You open a socket to an IP on port 80, you send your request, and you get back your response, and then you display the response. Except we just said we don't do that, right? Because the response is going to be just one HTML page, and we know there's all these other resources. So we actually have to do follow-up requests. So this is what the full picture looks like. We read the response. We parse the HTML to figure out what it contains. And we construct the DOM, which is the document object model, which is all the nodes that make up the page. And then we render the page based on this initial DOM. It might be missing some information. It might be missing some images, so there might be placeholders and things like that. But then we look at all the missing resources, and we fire out a bunch of requests for those. And then we just keep repeating that. We wait for because the responses from those might generate more requests, and we just need to keep waiting until they're all done. And then as they come back, we continue to render them into the page. That's the full process. And so there's like a full picture here of how that all works. So there's your DNS recursive step. You get back your IP of your server. You now know which server to contact. So you send your GET request to the server, and you get back your HTML for the first page. And then now you've discovered a whole bunch of additional resources that you need in order to render the page. So you fire off requests for those. In this case, let's just say there's a CSS and a CSS file and a logo. And then you get back responses for those at some point in the future. And hot pink is a real color in CSS. It actually is. There's a whole bunch of like names of CSS colors, which are just like really wild. Yeah, just like completely random names. It's pretty fun to look through the list. Okay, cool. So we have like 15 minutes left. Before we go on to cookies, is there any questions about anything HTTP related or DNS related? Okay, so we're not going to have time to get too much into cookies, but I'm going to give you a little preview, and we're going to get into the rest of it next time. So cookies, the cookies are really cool. So they let you do, like I mentioned before, they let you do authentication and like login and stuff like that. And there's all kinds of ways to attack cookies that are really fun and exciting. So this is how the server sets a cookie. It includes the set cookie header, and then there's this key value thing with an equals between it. You can set whatever cookies you want that you want the browser to basically remember and tell you going forward. So you can use it for things like preferences that the user has. Maybe you want to remember the user asked you to give them a dark theme on the website or whatever. And this will just get sent by the client. Now every single request to the same server is going to get this is going to get tacked on to that request. So let's actually look at this. So we're going to actually implement a server and see how this works. So the first thing I want to actually do is I'm going to make an HTML file for a page that we're going to serve to our user. What we're going to do here is we're going to implement basically a login system using cookies. So you can see how to do that. Hopefully we have time to do it. I can code fast. I think we can do it. Okay, so this page is going to just be, it's going to be pretty simple. It's just going to say, oh yeah, and we need to have a thing that we're building. So what kind of a site is this? Let's make it a bank. Okay, this is a bank login. So I better do good here. Okay, so we're going to say login to your bank account. All right. And so we're going to make a form. The form is going to post its response to a URL when the user submits it. And let's say we're going to make a login endpoint. So this is just going to be a URL that will log the user in. Cool. So now in the form, let's put an input for the username. Just like that. And we'll put another input in for password. Now, one thing that we can do with the password is we can make the type of the form actually password so that the letters they type show up as circles. Unless you guys don't want to do that. You want to see my password, but we can do that. Okay. Okay, so let's label these. This is not the nicest way to label these. There's a nicer way, but we need to go fast. So, ship it, do it live. A lean startup, This is a lean bank. All right. So we have a submit button here that actually logs the user in, and we named it login. Okay. So let's see what this looks like. I'm just gonna open the index file really quickly just to see what we built. Beautiful. Ship it. It's good enough to ship, right? I love it. Okay. All right. So now let's actually make the server component. So to do that, I'm going to use, so we could use the HTTP module, which is built into Node. It's just a little bit low level. I know we just implemented our own HTTP server with TCP sockets, but let's say we want to go a little faster here. So I'll use this package called Express. This is just a little sort of lightweight set of additions onto the Node HTTP package that makes things like dealing with cookies slightly easier than having to make the headers ourselves and stuff like that. But it's really not, there's not too much magic going on here. So the idea with Express is we need to, we're basically going to make a server, and you do that by just instantiating an instance of Express, and then you actually have to tell it what port to listen on. So we'll just say start listening on port 4000, and now we've just made an HTTP server. Great. Let's test it out and see if it works. So the way we do that is we need to make what's called a route. This is basically just a fancy it's like you have a bunch of switch cases, and you're saying if the URL that the user is visiting matches this right here, then I want this function to run. Okay. And so I can add a bunch of these. I could say, we're going to later on we know we're going to need a login one, right? Because we want the user to be able to go to login. But there's one thing I need to add here, which is, didn't we say we were going to post to login, not get? So we have to change this to post. So the server is going to say if somebody makes a post request and it matches /login, then go ahead and run this function here to respond to them. Okay. Now we need to talk about what is rec and res. So rec is the request, and res is going to be our response. So with rec, we can learn things like what is the URL the user's on, although I guess that's kind of obvious because it matched this. But you can also look up other things about the request, like the headers, for example, that's on there, stuff like that. Okay, so let's do, let's see, what do we need to do here? What I want to do is I want to load the home page. So let's import this thing called fs. This is the file system module, and I'm going to import a function called createReadStream. This is one of those streams like we had from before. And what's cool about this is I can actually, what this is going to do is open up a file, open up the index.html file, and I'm going to send it out to the response. So the only reason why we're doing this is what I could do here is I could, what I could do here is I could just open up this file and read it in to a string, and then I could write it out over the socket, and that would work totally fine. The reason why I'm doing this is because this is just a slightly better way to do it. It means that what I'm doing instead is as I read pieces of it out, I send them across the socket as soon as I get them. And so if this were, say, like a 1 gigabyte file, a ginormous file, right? I wouldn't want to tell the user, hey, please wait. I'm reading this into memory, use up a gig of RAM, and then start to proceed to send it to them once I've done that. So it's just easier to just sort of send it along as you go, and that's what this is doing. It's piping it to the response object. Yeah.
What did the curly braces on your second line mean?
This one?
Yeah.
Oh, okay. So this is the equivalent of me writing this. It's equivalent of me writing that. So I'm basically saying get require fs and then pull this property off of it and then make it available. It's literally the same as this line. Does that make sense to everybody? It's just a little bit fancy way of doing that. So I'll leave this here. I'll comment it out so you can see that. Okay, so now we should have a home page. So let me save this and let's actually start up the server. So I'll do node server. I could do server.js. Yeah, so now if I go to my browser on port 4000, I should actually have a real server serving me the same page as before. Okay, cool. Now what should we do? Well, we need to implement the login endpoint, right? Let's try to do that. So first of all, we're going to need to do one thing. So I want to make it slightly easier to read in this whatever I submit here. So let's actually see what happens when I type in a username here. I'll type in Alice and password. So if I log in, I should have done that before okay, let me refresh. I'll do it again. Alice, password. So what happened here is I posted, this is hard to see. Let me close some things here. Okay. So can everyone see what I did. So I posted to this URL, and the form data is right here. It's this username and Alice got posted. Now, unfortunately, it's not nicely formatted like this. It's more like this. That's what actually got sent to the server. Does everyone see that? That's a little bit annoying. I don't want to parse that myself. We could, but why? So, so to make it slightly easier, I'm going to import this thing called body parser. This is part of Express that is shipped as a separate module. And so all what I do now is, up here I'm going to tell Express to use the body parser. So and there's just one option I'm going to pass here so it doesn't yell at me. It's not really important what that does. But now what I can do is in here, I can actually, let's like console log out request body. So now there's this magical body property that got added to the request. That's going to be a nice object with the key and value, username and password that the user posted to that URL. Okay, so now if I go back to my browser and actually I need to restart the server too. So one trick I'm going to do here is I'm going to use this thing called nodemon, which will automatically restart the server anytime any files change in the folder that I'm currently in. So if we run that, now the server should have started up, and now I can go ahead and try that again. So I'll type Alice, and I'm not going to tell you what I'm typing for my password. Okay, so that looks like it's submitted. Oh, okay. Dang it. Got to be careful. Okay, so now we can see here what happened is it printed out. I guess that was from before when I reloaded the page or something. I don't know why that got printed, but this is what actually the request body is, right? So now I have this nice object. I can just get the username and password. So what should I do with this? One thing we can do is let's make a user database. So this is really fancy technology. It's called ObjectDB. So here's my database of users. Okay, what should Bob's password be? What's your favorite weak password? Hunter 2. Okay. Guessed. Yeah, that's a good one too. Okay, so now we have 2 users. Now what I'm going to do is when the user goes to log in, I'm going to get the username off of the body. And I'm going to say, okay, so that's the user you're trying to log in as. Okay, what's their actual password? Well, I looked that up in the users object, and now I know, okay, the user they're trying to log in and what the real password is. And then I'm going to say, if the request body's password matches password that it's supposed to match, then I'm going to, on the response, add a header. Actually, how about instead of doing that, I use the cookie function. It'll do it for us. It'll add the set cookie header. Now all I have to do is give it a cookie name and a cookie value. So what should we set here as the cookie name and value? Let's do something really, really naive at first. Well, if we did signed in, then we wouldn't know who was signed in, right? Username and the user. How about, what was that?
Like if the key is signed in and the value is something that represents the user.
Yeah. So let's just call it username for simplicity, and then we'll make it be the user's username that they're logged in as. How about that? Okay. So now let's respond with something. Let's tell them, if they logged in successfully, let's tell them, nice. Otherwise, let's tell them fail. Okay. Cool. Let's see if that works. So the server automatically restarted. I'll just refresh. Oh wait, what? How am I? Nice. Oh, I refreshed. It resent the same password I typed in before. Okay. Let's do that again. So I'll go to the home page. I'll type in Alice password. Nice. Okay. And if I do it again, but I do it wrong, fail. Okay. So it works. It works. Okay. So now. So we're detecting this correctly, but did we see if the cookie was set correctly? We didn't. So let's see what happened there. Right. So because remember we said if we get the password correct, we're trying to send this cookie down to them, right? So let's see if that worked. So type Alice password login. Okay. So now if I look at the request, I should see in the response set cookie username Alice. Don't worry about path. We'll talk about that later. But this is the server telling me, remember that you are Alice, and tell me that every time you talk to me again. So now if I go to the home page and I load that up, we should see in this request, even though it doesn't look like I'm logged in because the server's not doing anything with it, the request should contain cookie username Alice, which it does. Great. So let's use that to log in Alice when it's present, right? So how can we do that? Well, we need to import a thing called cookie parser really quickly because I don't want to parse the cookie. And I just type app.use cookie parser to have it do that for me. And now, just because I did that, I now magically have a thing called rec.cookie, which gives me an object with all of the cookies that are on the request that I just got. And so what we're doing in here is this is for the home page. So when the user loads the home page, I'm going to say, who are they presenting themselves as? So I'll pull the username off of the cookie, right? And I'll say if there is a username, because this could be undefined. If there is a username, then I'm going to greet the user and tell them, something like, what should I say? I should say hi and then their name. How about that? So we'll send hi. This is just a way to include a variable in your string. So I'm going to say hi username. Okay? And otherwise, if there's no username, I'll just give them the login form like before, right? Make sense to everybody? Okay, so now if I refresh the page, my browser should remember that I'm logged in as Alice because that cookie is set. So if I refresh, I should just now magically be logged in as Alice. Great. A cookie parser, let's see. Oh, I imported it incorrectly. It's supposed to be like that. Okay, that was easy. Okay. Cannot read property username of undefined. What happened here? It's cookies. Rec.cookies. Okay. There we go. Hi, Alice. Okay, cool. So now if I come in here and I delete my cookies, you can see cookies, by the way, under the application tab. If you open up application and then you go cookies, you can see all the cookies that are set. And we see username and Alice here. So if I delete that and I refresh, get the login form again. Hooray. Okay, that's awesome. Except, is this secure? What can I do? What can an attacker do? Attach any username they want. Right, exactly. So if I go here and I say username, Bob, and I refresh, Bob. That was easy. Okay, so yeah, you'd be surprised how often people store important stuff like this in cookies, right? So the lesson here is you can't trust the client, right? You can't trust them to follow the steps that you want them to follow for your application, right? They can do whatever they want, and they can modify any of the state in the cookies. So we're just about out of time here, but we'll go ahead next time and we'll improve this so that it's better than what it is now. And we'll talk about other ways to attack cookies that are pretty fun. So I'll see you guys next week on Tuesday. And I'll be doing office hours right now after this, so if you want to follow me over to office hours, you can. Cool, thanks.